All right, let's get through this content so we can work on some lab stuff. So here at the end of chapter 1, they're presenting a method to solve problems involving units. It's called a conversion factor or unit conversion method. The idea here is mathematically, if we take a value and we want to express that value differently, right? So in a conversion type question, like the one on the quiz, I'm giving you 3 liters of something and I want you to express that in grams. I wanted you to take, well, most of you did a really good job on that, to take that 3-liter quantity and say, for that amount, how many grams is that? Or how many grams is equal to that? So I wanted you to take that amount and not change the amount of it, but just to express that quantity with different units. To give different type of information about the same quantity. All right, so if I take a number, a quantity, and I multiply it by 1, it doesn't change the quantity. All right, so that's the idea behind the conversion factor method. So if I know the 2 quantities are equal, then I can put one over the other, or I could flip it. As long as they're equal, when I place one and divide it by the other, dividing 2 numbers that are equal gives me a value of 1. So now this is called a conversion factor, because when I take 2 values that are equal, dividing them makes it equal to 1, and I can multiply this by some other number, and multiplying a number by 1 also doesn't change it. So the idea here is I take some quantity, multiply it by a conversion factor that's equal to 1. If I multiply it by 1, it's still the same quantity, but I can work with the units and get the units to cancel out and give me the units I want. So the first thing you want to do with these, the simple ones we're going to work through today and the simple one on the quiz, you can probably get the answer working through those conversions in any number of ways. But when we get to more complicated conversions later in the semester that require 2, 3, 4, or 5 steps, where you've got to take a value and multiply it by like 5 of these conversion factors in a row to make sure all the units work out to the unit you want, it gets a little complicated if you don't set it up the way I'm prescribing. So this method is designed to be universal. Anytime you're converting one unit to another, you want to take this value and not change the amount, just change the units. You've got to multiply it by a conversion factor where the number on top and the number on bottom are equal to 1. So if I want to convert inches to meters, the first thing I want to do is to lay out what my conversion factors are. So right now I've got a number expressed in units of inches. I want to take that quantity, 12 inches, that distance. I don't want to change the distance, I just want to take that distance and express it in meters. So I'm going to take this 12 inches and multiply it by some conversion factors. I want to multiply it by things that are equal to 1. So I'm not changing the amount, I'm just changing the units. So if I want to multiply that by 1, I can multiply that by any factor where the thing on top is equal to the thing on bottom. So if I want to do that, I want to cancel the inches, and I want to get meters. However, I can't just put any numbers I want here. The number I put here and here have to be the correct numbers so that the top and the bottom are equal. If they're not equal, then it defeats the whole purpose of this method. The point is to multiply 12 inches by a value that's equal to 1, where the top number and the bottom number of the fraction are equal, so when I divide it equals 1. So in order to do that, I need to maybe work out my relationships first. This is especially helpful when you start to work with units you're not familiar with. Everyone in here has an idea of what an inch is and what a meter is, roughly at least. When we start to work with moles and molarity in units that you might not have experience with, it's going to be really helpful if you start the problem off by just laying out what your relationships are. You want to set up things that are equal, working with the units that are given in the question. So what do I know? Well, I know from the last slide that 1 inch equals 2.54 centimeters. So 1 inch equals 2.54 centimeters. That's a relationship. I can use that. I could put the inch on top and the centimeters on bottom, or the centimeters on top and the inch on bottom. Do I have the relationship I really want, though, which is a relationship between inches and meters? Is that given anywhere? Do you know that offhand? Do you have that relationship on the formula sheet? If that's ultimately what you want to convert, inches into meters, if we had a direct relationship between those two given to us, that would be ideal. We'd only need to do one step in the conversion. But we don't really have that, so what we'll have to do first is to convert the inches to centimeters using this relationship. Then I'll need a second conversion, because ultimately the question is asking about meters. So I'll need another relationship, and I'll have to set that up between centimeters and meters. And again, I have to make the top and the bottom equal, so I'm multiplying by 1 and not changing the amount, just changing the units. So what's that relationship? I'll work that out, set that up. So I want the relationship between meters and centimeters. How do I figure that out? That's on the metric table. That is on your formula sheet. You don't have to memorize that. So in the metric table, there's the base unit. That's 10 to the 0, which is equal to 1. Then so that would be meters. That's the base unit for length. Then there's centimeters, and the power of 10 on the formula sheet table says that that's 10 to the negative second. So when you're doing these metric conversions, there's a number of ways you can do them. I noticed people doing them differently on their quiz answers, and mostly you were getting the correct answer. So if you have a method you like, that's fine. What I recommend, though, which will work every time, is if you're trying to convert between two different metric units, just look at the powers of 10 and subtract them, and then make the number positive. So 0 minus negative 2, or negative 2 minus 0. It doesn't matter what order I subtract them in. I'm just going to subtract them because I want to know what the difference is between these powers of 10. What's the magnitude difference between meters and centimeters? So when I do the subtraction, I get a difference of 2 powers of 10. The relationship is 10 to the second. So if I'm setting these equal, whatever unit is closer to the bottom of the table is the smaller unit. So I'll take the difference in the powers of 10, make that a positive value, and make that positive power of 10 equal to 1 of the larger units. So whatever the difference is in the power of 10, 2 powers of 10 difference, I'll take 2 to the second power, then make it a positive 2, put it with the smaller unit, and then it will be equal to one of the larger units. Right? Because a positive power is a large number. 2 to the second is like 100. There's 100 centimeters in 1 meter. So now I've got my relationships worked out. I just have to put them in to my conversions and get the answer. So 1 meter equals 10 to the second centimeters. 1 inch equals 2.54 centimeters. Now I can see for sure my inches canceling, my centimeters canceling, and I've got the unit I want in the end. It's the only one that's not canceled. So then I would just plug that into my calculator, 12 times 2.54 divided by 10 to the second. So what I would type in my calculator is 12 times 2.54 divided by E2. And I get 0.3. I'm limited in terms of sig figs. How many sig figs does this relationship, the metric relationship, have? The value 10 to the second has unlimited. It's an exact value based on the definition of what a meter and a centimeter is. It's not limiting me at all. It's infinite sig figs. That's not going to limit my sig figs. This number has 3 sig figs. This number has 4 sig figs. So my answer should be limited to 3 sig figs. So I got 0.305. That's my answer. Questions about that? I'm telling you, if you use this method, it's going to, don't take any shortcuts, because once we get to much more complicated questions where you've got to do lots of steps, you know, it's really helpful to have these relationships worked out first. It's also critical to show the units so you can see which ones are canceling. Inches divided by inches, something divided by itself cancels out. Centimeters canceling, I've got meters left over. I mean, that's the only way to know for sure that you set it up right, is to see all the undesired units canceling and to know that the only units left are the units you wanted to express that value in. So let's look at a couple other examples here. So we want to convert kilometers to micro, or kiloliters to microliters. So there's another example using the metric system. This is only one conversion required, but if we have 4.35 times 10 to the minus fourth kiloliters, I want to express that in microliters. So I need a conversion. So what most textbooks do is they multiply this number by something in a parenthesis. I don't like to put these time signs in here because sometimes you'll be doing a calculation with a variable, like using some algebra, and you might have x as your variable, and that gets confusing. So instead of doing that, like instead of multiplying this by some conversion, I personally feel it looks cleaner if I just make a grid where I can multiply everything on top and divide everything on the bottom. It's the same thing. If you don't like that, you don't have to use it, but that's what I like to do. So what I need is a relationship where I can cancel kiloliters and get microliters. So the prefix for micro is like a Greek symbol called mu. So I need that relationship. So I need to look on the metric table. The micro prefix is 10 to the minus sixth. The kilo prefix is 10 to the third. So the number of powers of 10 difference between that is 9. 3 minus negative 6, or negative 6 minus 3. Either way, I get 9 once I make it positive. So the relationship here is between microliters and kiloliters is 9 powers of 10. If I make that at 10 to the positive ninth and put it with the smaller unit, then they'll be equal. So that way I don't have to mess around with any negative powers of 10. All my powers of 10 are positive, and I always put them with the smaller unit. So I need a large number of these smaller units to make it equal to one of the larger units. And so I would put that here now to make it equal. Again, my metric relationships are exact based on definition, so they're not going to limit my sig figs. So I just have to multiply that in my calculator, and I get 4.35 times 10 to the fifth microliters. Questions about that one? All right, let's look at a couple more conversions. So I'll look at 1.50b. It's on page 26. And let's skip that one. It's really similar to the one we just did. Let's look at D. 10.6 kilograms per meter cubed. That's another thing. When you see a unit like this, like if you're looking at a density or something like 5.0 grams per milliliter, you probably should get in the habit of just writing that down as 5.0 grams per milliliter. Because if you keep it like this and then you set up your conversion, it's going to make it possibly look to you like the milliliter is on top of the fraction, and in order to cancel it, you need it here. That's not correct, right? Because I've got this dividing here. That means the milliliter is actually on the bottom of the fraction. To cancel it, I need a milliliter on top of the fraction. So in this case, I've got kilograms per meter cubed. I want to convert that to grams per centimeter cubed. So let me actually get a little bit more space. 10.6 grams per meter cubed. I want to convert that to kilograms per meter cubed. I want to convert that to grams per centimeter cubed. So here I've got to do a couple different conversions. Those are going to require some relationships, right? So I'm going to take this initial value I have, the 10.6, and I'm going to multiply it by some factors where the top and the bottom are equal, so I'm not changing the amount, I'm just changing the units. So I need to develop those relationships. I need to develop the relationships where two things are equal so I can put one over the top of the other. So I want to convert, and actually what I also like to do is instead of writing it like this and showing that I want to convert this into that, which is true, when I put this here, it kind of blocks off my paper and I've got nowhere to set up my conversion. So what I prefer to do instead is to kind of think about this in the form of a question. What is it really asking? Really, it's asking how many grams per centimeter cubed would be equal to 10.6 kilograms per meter cubed. Right, so now, writing it out this way, it's got a couple benefits. One, I can think about what the question is really asking. Two, I see what units I have and what units I want, and I'm always focused on that. Focusing on the units is the key here. If you lose track of the units, you have no idea what direction you're going in. Like looking at the units makes me realize I need a relationship to get from what I have in kilograms to what I want in grams. And I need a relationship between meters cubed and centimeters cubed. I like to establish those relationships before I start plugging things in. Because if I don't have the relationships correct, then plugging in is not going to help me. So I've got kilograms, I want grams. I need a relationship between those two. What's the relationship between kilograms and grams? Well, kilo is 10 to the minus third, or 10 to the third. Grams is 10 to the 0, the base unit. So there are 3 powers of 10 difference. So I'll make that a positive 3. I put it with the smaller of the two values to make them equal. 10 to the third grams equals 1 kilogram. If you make 10 to the third kilograms equal 1 gram, that's not right. Kilograms are already larger. 1,000 of the larger things not going to be equal to one really small thing. So that's one relationship. Now I need a relationship between centimeter cubed and meter cubed. That's a little bit tricky. The metric table has centimeters and meters. Centimeter is 10 to the minus second, meter is 10 to the 0. So I know the relationship between centimeters and meters, but if I'm going to get the relationship between them cubed, that's going to require a little bit of math. Right? So if I want the centimeter to meter relationship, that comes from the metric table. There are 2 powers of 10 difference between them. So I'll take 10 to the second of the smaller units, set that equal to 1 of the larger units. So there's 2 power of 10 difference between centimeters and meters. If I want centimeters cubed and meters cubed, then I have to cube both sides of this equal sign. It'll still be equal as long as I do it to both sides. If I want the units cubed, I need to establish the relationship first and then cube both sides. So centimeters becomes centimeters cubed. Meters becomes meters cubed. What do I get when I take 1 cubed? I still get 1. What do I get when I take 10 to the second cubed? 10 to the sixth. 10 to the second times 10 to the second times 10 to the second gives me 10 to the sixth. So there's actually 10 to the sixth centimeters cubed in every 1 meter cubed. So now I've got the relationships I need worked out. I just have to plug them in here. And this is nice because I've got my goal already written down. I just need to set this up so when I multiply that 10.6 kilograms per meter cubed by my first conversion factor, I'm canceling some units. So maybe I want to cancel the kilograms first. I determined 1 kilogram equals, this doesn't really look very clear, 10 to the third grams. So that's one relationship. The kilograms now cancel. I've got the unit I want on top, so I don't need to do anything more with that. But the unit on the bottom is not correct, so I need to cancel the meters cubed. It's already there, so I need it on top to cancel it out. And I need the centimeters cubed on the bottom. So I want to put this value here and this value up here to make it equal 10 to the 6th centimeter cubed equals 1 meter cubed. Then I would just plug it in my calculator. I would do 10.6 times E3 divided by E6. If you can't find your E button, you can always let me know. I'll show you where it is on your calculator. So again, my metric relationships do not limit my sig figs, but I've got 3 sig figs here. So the rule for multiplying and dividing is I am limited to the one that had the fewest, and the fewest is 3. And so again, also I want to make sure I see everything canceling. So I only include the units I have that didn't cancel out. 3 sig figs with the correct units. Questions about that? All right, let's look at this worked example then. Here I've got 5.2 liters of blood. I want to know what the volume is in cubic meters. So the question is, how many cubic meters or meters cubed is equal to 5.2 liters of blood? It doesn't have to be blood, it could be anything. So I need some relationships. What relationships do I need? Help me out. What relationships might be useful here? It'd be nice if I knew exactly how many meters cubed are in 1 liter. That would be nice. Can I get that from the metric table? Is that a definition that I know? No. So I need some other relationships that will help me bridge the gap between meters cubed and liters. Okay, so yeah, I can do 1 liter equals 1,000 centimeters cubed. If that wasn't given, to me, is there anything we talked about that I could have used there? The back? What? Yeah, I know 1 milliliter equals 1 centimeter cubed. That is a definition. Right, so that's a relationship I can use. And I know that the liter is the base unit and a milliliter is 10 to the minus third. So if I want to set those equal, there's a 3 power 10 difference. I put that as a positive 3 with the smaller unit equal to 1 of the larger units. So there are a number of different ways. Makes it look like an 8. There are a number of different ways I can set up these relationships, but I'd like to not have to remember a bunch of stuff. I'd like to be able to set them up just from the metric table, and maybe a few limited things I remember, such as the definition of a milliliter is that it is equal to a centimeter cubed. I still need a meter cubed though, right? So we did that one on the last slide, or on the last example. We said 1 meter cubed equals 10 to the 6th centimeter cubed. So maybe I think I have all the relationships I need. I want to start working. So I want to get the liters to cancel. So maybe I'll use this one since this comes directly from the metric table. I'd probably be more likely to work it out that way if I didn't have any given information. 1 liter equals 10 to the 3rd milliliters. Always, the whole time, thinking about what units I'm trying to get in the end. So now I've got milliliters. I want to cancel that and get closer to the meters cubed. So I would look at going from milliliters to centimeters cubed. Then I would go from centimeters cubed to meters cubed. So I can cancel out these units I don't want. I got the units I want. Now it's just a matter of plugging into my calculator. And you can start to see where, as these begin to be more and more complicated, with more and more conversions necessary, it's really helpful to have the relationships written out beforehand, and it's really helpful to show all the units written down. Don't just show me the numbers, especially on an exam, where if you don't get the number correct, maybe you made some silly mistake. If I don't see your work and I can't see your units canceling, it's really hard for me to give you the partial credit that you might deserve for knowing what you know. So just make sure you include as much as you can so I can give you credit for what you've done. So then I would just plug in 5.2 times E3 divided by E6, and I get 0.0052 meters cubed. Two sig figs because I was limited by the 2 sig figs I started with. Questions about that? Okay, here's another one. Here's some density calculations. So here I've got some ice, and the density of ice is not given to me. I want to calculate that. So if I want to calculate density, what units do I need? For density, I need some unit of mass over some unit of volume. I'm given the mass, right? So really, I can set this up and say, for this ice, what is the mass over the volume? What I've got is 7.36 grams for the mass. How do I calculate the volume? So I can plug that in. Right. Exactly. So because the shape is an exact cube, I know a cube's volume will be equal to the length times the width times the height. And if it's a cube, all sides are equal length. So it should be 2 centimeters, and I have to cube that. So that's going to mean I have to cube the 2, and I have to cube the unit. So that's pretty straightforward. So I'm going to have 7.36 grams over 2 cubed, which is 8. I'm cubing the 2 and I'm cubing the unit. So my units become gram per centimeter cubed. That's a unit of density because it's a unit of mass over volume, so that's fine. So I just would divide 7.36 divided by that 8.0, and I get 0.92. Limited to 2 sig figs because I started with 2 sig figs in the 2.0 grams per centimeter cubed for my units. So that's the density of this ice cube. That's part A. Part B, we want the volume if we had 23 grams. So what would, in this case in part B, it doesn't tell us what units to use. So we can use whatever units are most convenient to us for volume. So what's the most convenient unit to use for volume? Probably in this case centimeters cubed, because I've already got some information involving that unit. So the question in part B becomes how many centimeters cubed is equal to 23 grams. So if I had 23 grams of ice, what volume will that take up? How much space will that take up? I want to express that amount just with different units. So again, I need a conversion that will cancel the grams and get me my other units, but in order for it to work, whatever I put on the top has to be equal to whatever I put on the bottom of this conversion. So how do I get the relationship here? Well, the density is a relationship. Anytime you're given a number like this that has units, where I've got one unit over another unit, that is a relationship. You can express that as 0.92 grams equals 1 centimeter cubed. That's what that density tells me. If I have 1 centimeter cubed of it, it's equal to 0.92 grams. That's a relationship. And if I want to convert grams of something that's a pure substance into the volume of that substance, the density is the relationship I need. It's got to be given to me. So since I calculated it in part A, I can use it in part B. So this is my relationship I need. I only need to use one conversion. I want the grams on the bottom so they'll cancel. And so then I would just divide, and I get 25 centimeters cubed. Questions about that? So when you see in a problem that you're dealing with, if you're given a value like this density with one unit per another unit, just immediately write that down as a relationship. There's very unlikely that they would give you that number with those units if they didn't expect you to use it as a relationship. There will be lots of other things other than density that we'll be using that will be one unit per another unit. So you want to get into the habit of thinking of that as a relationship, because if you can think of that as a relationship, you'll realize I've got to use this as a conversion. I've got to put either grams over centimeters cubed or centimeters cubed over grams to get the units to work out. Let's do maybe one more density example. Let's look at 1.68. So 1.24, 1.28 are pretty straightforward. You should have opportunities to practice with ones like those. But if you want to work on these, since they're even numbers, the answers aren't in the back. If you want me to look over your work, make sure you're doing those properly, that's fine. But most of you did pretty good on the quiz, so I'm not going to go through the most simplest examples and bore you to death. So if we look at 1.68, though, this is a good question. It relates to what you've been doing a little bit, probably with the densities for your unknown metal in the lab. So this question says you've got a piece of metal. It tells you the mass, so we would assume that this piece of metal was weighed on the balance, and its mass is given as 13.2 grams. What's the problem with that? If you write in your lab report that your metal had a mass of 13.2 grams, that's going to be a bit of a problem. Why is that unreasonable? Yeah, it has to do with the sig figs. If you're using the balances we have, they give you 3 decimal places. So if you put your metal on the balance and it reads 13.2 grams, that's not what you're going to see on the screen. The screen might say 13.200, But those zeros are significant. It's telling you that they're zeros. They're not completely unknown. They do have some significance. So make sure you include all the decimal places that you have some information about. In this case, whatever balance this person used wasn't very good. It only gave one decimal place of information, unfortunately, so that's limited us to 3 sig figs. Then it says it was dropped in the graduated cylinder, and the volume initial was 17 milliliters on the graduated cylinder. They show a picture of that. You can see the meniscus is right. Actually, they don't show a picture of that. They show a picture of it after the metal was dropped in. So they're telling us they read the volume at 17.00 milliliters. Then they drop in the metal, and they show us a picture of what it should look like, or what the graduated cylinder looks like after they drop the metal in. So when we're looking at the meniscus, we got to eyeball this. The key thing here is that there are graduations between 18 and 19. It looks like there's a graduation at every 0.1 milliliters. And looking at the meniscus, it looks like it's just above the 18.4. So again, with the sig figs, when you have a device like this that's graduated with these markings on the side, you've got to look at where the markings are and make sure you include all the information you're totally sure about, plus one that is somewhat of an estimate but still significant or important because you still have some information about it. So we're sure that the volume final, once the metal was dropped, is between 18 and 19, right? There's no question about that. Do we have certainty about what the first decimal place should be or what the next digit is? Do we have any information about it at all? Yeah, we have some information about it. It's not 18.9, right? It's about 18.4. So that digit is also significant. Do I have significance about the next digit? I don't have complete certainty about it, but I still can say something about it. I mean, the picture is better than my drawing, but if you look at the picture in the book, you could. We're judging the volume from the bottom of the meniscus, not any somewhere else, right? So that allows me to line things up pretty carefully. If I look closely in that picture, it looks like it's significantly closer to the 18.4 than it is to the 18.5. If I can tell that, I have some information about it. I can make an educated estimate that is significant or important. So the next digit I need, I can't just ignore it. I have some information about it. I need to include it. So it's an estimate, though. It might not be perfectly exact, but it's still, I can tell it's not 18.49 or 18.48. It looks like it's closer to 18.41 or 18.42. So it's important. It's significant. I got to include that digit, whatever I think it is. And you might disagree with other people if they're looking at that, but your number is going to be at least somewhat closer there. And so that's an estimate. People know that. When you make a measurement, whatever the last significant digit is that's reported, people know it's a little bit of uncertainty in that digit. So I've got the mass of the metal. I want the volume of the metal. It's going to be the final volume minus the initial volume. So when I subtract, I get the volume of the metal. So here I want the density of the metal. So it's going to be the mass over the volume. Both those numbers have 3 sig figs, so I'll be limited to 3 sig figs with my answer 9.30 grams per milliliter. My calculator read 9.295. Limiting that to 3 sig figs, I've got to use the 5 to round. So rounding the 9 up gets me to 9.30. But I still have to include all 3 of those digits because they're all significant since I had information about the numbers I plugged in to get them. And then just again to point out, once I've got the density, that is a relationship. That can be used now to convert any volume for this type of metal into a mass, or any mass into a volume.